Thank you very much. So, yeah, it's an honor to be here, of course, in this conference. So, first, just a few words. I know Christophe, well, I knew him from a long time by name, but I know him especially from my time I spent a long period here in Lyon in 2019, where I had a lot of very nice and inspiring discussions with Christophe. And, well, some of the topics I will present were things that we discussed together. So, yes, what I want to talk about is ideas of hydrodynamics. And I guess the point I want to make is that a lot of the hydrodynamic structures are very universal, can be applied to very different systems, and lead to very powerful results about emergent behaviors in many body systems. Okay? So, it's going to be divided in, well, 4 parts. Apart from introduction, I'm going to talk about generalized hydrodynamics, which is a hydrodynamic theory for integrable systems. And then, so these are 3 kind of loosely connected parts. So second part, I will go into a linear response and hydrodynamic projection, where one can see that these principles from hydro can be applied very, very widely, not just in integrable systems, chaotic systems, but very generally. And the last bit, I'm going to talk about fluctuations, where one can see that hydrodynamic ideas give a lot of very powerful results beyond linear response. So the first thing, I talked about hydrodynamics, so what I want to describe with that is large-scale behaviors. So I imagine that I have, say, a system. Here I'm writing a system of particles in interaction, but it can be a system of spins or field theory or anything. And you prepare it, say, in 2 different temperatures, T left and T right. It doesn't have to be a sharp connection there. It can be something smoother. You want to see what happens with the system as it evolves in time. So this is kind of a unitary evolution, if you wish. And this is really an out of equilibrium behavior. Eventually, for instance, you'd like to calculate the currents or, in fact, the whole profiles. Okay. Now, how do you do? Well, there is a kind of very well-known way of doing that, and it's using hydrodynamics. So if you have a system of interacting particles, typical interacting particles, you will write the hydro equation. This is in 1 dimension. And this is conservation of mass, and it's conservation of momentum, or earlier equation. There's a pressure that's involved here, which is the equation of state for your system. Once you know that, you write this equation, and you can solve them for the 2-temperature problem. That's called the Riemann problem. There's a lot of nice theory about these hyperbolic equations to solve this kind of Riemann problem. Shocks may develop, or kind of fan rarefaction waves and things like that. So this is quite a, once you know that, you kind of have solved the problem. Okay? But this, of course, works for interacting systems. If your system is not interacting, well, you write a different, this is wrong, you write a different equation. You write the Liouville equation for conservation of phase space, which can be seen as, the equation you would get from an empirical density of particles from some kind of typical initial state, and your empirical density at large scales would converge to some kind of weakly to some smooth function which satisfies the Liouville equation. Okay? So these are 2 different equations. Now, there are 2 things I want to say about that. First of all, of course, these 2 equations are very different in nature. One is a kinetic equation type of thing, right? So you can think of that as a collisionless Boltzmann equation, kinetic equation. The other is a hydrodynamic equation, which seems to come from very different principles. So one point that I would like to make is that actually these 2 equations have a very similar origin. Both can be seen as some kind of earlier hydrodynamic equation, even the kinetic equation. And the other thing that I want to say is that actually there are many systems that don't fall within neither of these classes. In particular, if you go in the lab and do these kind of cold atom experiments where rubidium atoms are constrained to be in 1 dimension, they are described by something called the Lieb-Vinegar model. This model is integrable. It has infinitely many conserved quantities, local conserved currents, and it is interacting, so that equation is wrong, and it is integrable, so that equation is also wrong. So actually, it does not fall into neither of these classes, so in order to solve this model, you have to do something else. Now, of course, the Lieb-Vinegar model is integrable, usually also referred to as exactly solvable, but it happens that for exactly solvable models, sometimes you don't know the exact solution, and indeed, you don't know the exact solution for this 2-temperature problem from Bethe and Satz. It's kind of not possible to find it. You need some other principles. Okay? So the principles are those of hydrodynamics, and what I want to claim here is that actually very general principles. So what are the ideas? Well, you have your system, many body system, you can look in space-time, and the assumption that you make is that at least at large enough space and times, when the system has time to relax, the system will go to some kind of relaxed state, maximal entropy state, where entropy is maximized with respect to all available extensive conserved quantities. Okay? So these are my Qn, they're extensive, there's some kind of density. And you assume, it's an assumption, maybe you'd want to prove that, but it's hard to prove mathematically. You assume that everywhere in space-time, your system is more or less described by this kind of Gibbs-like ensemble. In integrable systems, you have infinite sums here because you have infinitely many conserved quantities. It's called the generalized Gibbs ensemble in this case. Okay? This is the assumption. So in equation, what you would write is simply that any average of local observable is, to good approximations, hydro approximation, described by an average of that same observable in a space-time dependent generalized Gibbs ensembles or maximal entropy state, where all the betas, the inverse temperature, chemical potential, whatever, depends on x and t in some way that you don't know yet. And what you write, in order to know how they depend, well, you just write the conservation laws. So these are the conservation laws. You write them for these averages after doing the hydro approximation. So this is it, right? This is Euler hydrodynamics in its general formulation, right? Now, you see that it's an equation for all these betas, and there are as many betas, temperatures, as there are extensive conserved quantities, so as there are Qn. So this is kind of looks like you have enough equation for unknown functions, okay? Now, one thing to note is that although you made this approximation for local observable, it is in general not true, it is incorrect, that if you start with a state that is, with varying temperature, slowly varying temperature profile in space, you let it evolve, it is not true that it becomes a state with slowly varying temperature and other, generalized temperature profile at later time. This is not the correct description of the state on a time slice t. It is correct for local observables. It's not correct for correlations. Correlations develop, and these can be described by another theory beyond this simple approximation. Well, in fact, can be based on that. But for local observables, this is sufficient. It's important to realize that, this is just for local observables. Okay? Now, once you have that, you can develop the structure of Euler hydrodynamics. So in general, there's a bijection between the betas within some regions and the average densities within some regions, so the temperatures, chemical potential, and average energy, average particle number, etc. Okay? And with this bijection, you can always write the currents as functions of the densities. These are the equations of state. That includes, for instance, the pressure, which is momentum current, as function of particle density. Okay? So you write this, and then you can, by constructing this flux Jacobian, which is just the derivative of current with respect to densities, you get the so-called quasi-linear form of the Euler equations. Okay? So this is the basic structure. And the claim is that it's very general and can tell you a lot about the emergent behaviors in many-body systems. Okay? In particular, the spectrum of this A matrix is interpreted as the velocities of the sound modes, or what we call hydrodynamic modes that you have. Okay? Now, so this is structure, and if you apply that to a typical interacting gas, where you have, say, just conserved densities and conserved momentum, then you do get back the standard equation with the pressure if you use Galilean invariance, for instance. So that includes this. But it's more general, and in principle, it describes many systems. Now, what you need to know to use that, well, you need to know this manifold of maximal entropy states. You need to know what are the states which corresponds to relaxation. So supposedly, these would be the stationary state, which are also homogeneous in space, and which cluster, so whose correlations decay fast enough in space. So that's the set of state you need. Once you know that, you plug it in your equation and you have your Euler hydrodynamics, essentially. Okay? So it's a movement in some manifold of state. Now, I'd like to solve this problem for integrable system to show you how this works and give you kind of the solution to these cold atom gases described by the Liebniger model. Right? Now, so integrable system, let me start actually with the simplest one, which is the free particle system, where we can apply blindly, naively, all these principles, and we recover the Liouville equation, just to show you how this works. An integrable system, it works very similarly, even with interaction. So without interaction, the conserved quantities are, well, actually, all the momenta are conserved if you don't have any interaction. So you can think at for every momentum, instead of index n, you have a continuous index p. Every momentum, you build this momentum density conserved quantity. And it has its own space density. This becomes a phase space density, which can be written explicitly like that for trajectories of particles, described by some Hamiltonian, for instance. Well, here, free Hamiltonian. Okay. Now, so with that, your maximal entropy states are described not by a set of parameters, by a whole function of momentum instead. So instead of writing beta and qn, you consider you measure on phase space, which is weighted by this Boltzmann way, where you just put some function that describes your state, that describes all the betas, on every of the momenta of the particles. Okay? And then your average densities are some function of the momenta. You use that, you make it space-time dependent according to earlier hydrodynamics principles. So now your state, your W becomes space-time dependent, and your densities as well. And then what you have to calculate is the equation of state. So the currents is very simple for free particles. The average currents, which you can write explicitly in that form, with P times that, is just P times rho P. The average currents is Pi times that, and Pi is fixed to P, so you get that. Right? So it's very simple what the average currents are. And if you put the densities and the currents together, you get the Liouville equation, right? So you reinterpret the Liouville equation as an Euler equation. Well, this is a bit of an academic exercise, if you wish, but you can do the same for integrable systems. So let me show you how this works for integrable systems. Now, integrability, well, okay, there's a lot of structure for integrable system, Lax matrix, R matrix, transfer matrix. Now that can be complicated, but in fact, the physics is extremely simple, and the construction I'm showing you is based on the physics. Very simple. What's the physics? Well, there's one important property of the integrable system that is always true in many body. Integrability is the idea of factorized scattering. So you have your system, your gas, interacting gas, and you look at what happens. We put it somewhere, and beyond it is emptiness. You look at what happens when you let the particles expand in positive, negative time points. So what you get is freely propagating particles. That's usual scattering process. But what's happening in integrability is that this scattering is factorized and elastic. That means that the set of out and in particles is the same, and the scattering is factorized into two-body scattering. You can write that quite explicitly in terms of trajectories again. So you have trajectories. You look at positive, negative time, they will look like that. Assume that your particles are interacting repulsively, for instance, for simplicity. If they are interacting attractively, then you would have bound state. You'd have to describe the bound state. Okay, well, in general, you can do that. So okay, you have that, and then elastic scattering tells you that a set of momenta is conserved, is the same in and out, and the impact parameters in this y and out are their difference is the scattering phase. This difference of impact parameters factorizes into a set of two-body scattering shifts. So the two-body scattering shifts, here you have a particle, another particle, they do something, they interact, and as they come out, the same momenta come out with some kind of shift between the positions of the trajectories. Well, in general, if you have a many-body process where a lot of things happen, very complicated, at the end, the shifts will just be a sum of two-body shifts, as if they had interacted in separate, well-separated two-body scattering events. Okay? So as if the interaction length was kind of time zero, or distance zero. So that's the basics of integrability. Now you can use that to do Euler hydrodynamics, indeed, surprisingly enough. So this does not work anymore. So I might have broken the machine, sorry. Yeah, I think it doesn't work, sorry. So I'm not sure, maybe the battery doesn't work, or yeah, that doesn't work. Yeah. I don't know. Maybe the battery is not good anymore. Ah, no, it's enough. Oh, good. Okay. Ah, here it is. Whew. Okay. So how do you do that? So the idea is very simple. The idea is this little gas of particle. Okay? I want to describe local kind of fluid cell, mesoscopic cell, where the system has thermalized. Okay? Now, the determinization is a generalized Gibbs ensemble. It has infinitely many temperatures now. That is a bit complicated to describe, right? However, there's a simplification that I can use. So I look at this fluid cell there, and I kind of extract the fluid cell and see what particles come out, what are the asymptotic momenta. The idea is that these asymptotic momenta are correct conserved quantities. So the distribution of momenta within the fluid cell is a correct conserved density. That's the idea, right? Now, really, to make sure that this is correct, I mean, this is passing from the the global scattering problem to a local fluid cell scattering problem, there's quite a bit more to say, but this is the basic assumption that we make in integrability, that you can look into a fluid cell, see what asymptotic momenta you come out of that, and these are correct asymptotic momenta that you would see actually in the whole system, the whole gas, if you let it expand for a long time. So these are correct asymptotic momenta. In other words, it's like if because interaction is local, actually within that you already have enough information of some bits of the asymptotic momenta. So these are conserved, and this is your conserved density in some, in phase space. So this is very similar to the free model. Okay? Now, if you want to relate that to all the betas, it's complicated, but it's done by the thermodynamic Bethe-Ansatz. It's been done from some time ago. So, but I don't need that. I don't need the betas in the end, right? I can just think about the conserved densities. So these are my conserved densities in that fluid cell. Right? But what I need, of course, is the equations of states, the currents. How do I calculate the currents? Well, it turns out that this is a really non-trivial calculation. Is what we found and other people found by different variety of model calculation, calculating the currents in GGEs. We found that you can just multiply your density by an appropriate velocity, not by p anymore, like in free model, by some non-trivial velocity, which depends on the state, rho p, and depends, of course, then on x and p, because it depends on rho p. So once you have that, you write the conservation equation, and these are the GHD equations. So these are the Euler equations for integrable systems. What is this effective velocity? Let me show you the formula. It's not just it's an explicit formula, but it involves the fact that you should solve a linear integral equation. Effective velocity is explicitly written as the solution to this linear integral equation, which involves the density and the two-body scattering phase. Because scattering is factorized in two-body scattering shifts, that's all you need in order to describe the full exact average of currents. That's the only dynamical information that you need, two-body scattering shift. Once you have that, you solve this. Where does this equation come from? Well, it has a very simple picture. Imagine your particles going around and accumulating time delays of phase shifts, and you assume that they accumulate them into well-separated process. You look at what happens with the particles as it accumulates these time delays. Well, it goes some distance with its bare velocity, accumulate time delays, goes some distance, accumulate time delays, and overall, it accumulates some kind of overall velocity, which is different from its bare velocity, say the momentum p. That different velocity, you can evaluate it by a simple back-of-the-envelope calculation, where this difference of Vf is kind of the probability that two particles of momentum p and p prime collide with each other and then accumulate a phase shift. And this is the density of particles p prime, and this is the phase shift that particle p acquires when it meets a p prime. So this is essentially the velocity that a tracer particle that follows the asymptotic momentum p would see as it goes in the gas. And the idea is just have to multiply your density of particle by this to get the exact current. Now, this formula for the current was obtained in many different works, in particular in 2003, 2005 in soliton gases, where people studied gases of KdV solitons and looked at the hydrodynamics. So the same picture holds when you look at the gas of KdV solitons. And then later on in quantum models where it's been derived using Bethe-Ansatz, algebraic Bethe-Ansatz, and other techniques. But the result is that. So once you have that, then you can do hydrodynamics. I just want to give you a bit of an intuition of how this works, in fact, in the Liebig model that describes cold atom gases. So there you have an explicit Bethe-Ansatz wave function for the Liebig model. So this is the model, delta function contact interaction. This is the explicit Bethe-Ansatz wave function, like a free wave function with some kind of phase that describes the interaction, that describes the two-body scattering, actually. And from that, you can calculate, in particular, the semi-classical scattering shift, which is the thing that will be involved in the GHD equation. Now, this is just a wave function. How do you do hydrodynamics from that? Well, you can do something very simple. You can just modulate the wave function, modulate the amplitude with kind of slowly modulating functions of x. That's not too bad because in quantum system, a given single wave function actually is believed to represent a whole GGE by the eigenstate thermalization hypothesis. So these momenta there actually describe what's happening in your fluid cells. In fact, these momenta are the asymptotic momenta of these interacting systems. And these phi's are the two-body scattering shifts. So the wave function encodes already a lot of information, so you can just slowly modulate it and see what happens. As it turns out, if you follow the the top of the wave packets, you might imagine you modulated with different wave packets. Well, these wave packets satisfy a simple classical equation, so the time evolution of the wave function is described by evolution of these wave packets in this kind of slowly varying function. And these wave packets satisfy a simple equation, which is kind of nonlinear equation that has very specific trajectories where you accumulate time delays. And if you look at that as a classical dynamical system of trajectories and do the kind of empirical density and then kind of a weak limit, you recover the GHD equation exactly. So actually the equations of generalized hydrodynamics can be seen as equation of a gas of wave packets which interact with each other according to here in the Lieb-Deniger interaction. So once you have that, you can do the full hydrodynamics. So you realize that these wave packets are the hydrodynamic modes. The spectrum of the A matrix is the effective velocities, continuous. And you can write the normal modes of this hydrodynamics so by defining n in terms of rho in some specific way, you kind of diagonalize the hydro. That allows you actually to solve the Riemann problem of hydrodynamics for this GHD equation. You can also add the force term and add diffusion. So the force term, this equation then can be verified in cold atom experiments where you have an external potentials. And diffusion you can add, which is important when you start having a kind of stronger variation in space. And now this can be verified in the numerical, for instance, TD-MRG calculation from integrable quantum chains. So here I did the quantum particles, but you can also do that for quantum chain. So that shows you that the ideas of hydrodynamics actually do not require chaos, do not require kind of a very strong constraints on your system, on your many-body systems. You can apply that to integrable systems and you get a nice equation for emergent behaviors at large scales. So they are very general. Okay. So that was my part one. The part two that I want to do is, well, okay, so this is nice. You would see how densities evolve in space-time. But one of the important things about hydrodynamics that hydrodynamics predicts is something obtained from linearized hydrodynamics, now the correlation functions, where you see a lot more of the physics. So again, let me come back now to the basic kind of general structure of Euler hydro with this kind of A matrix and the general Euler hydrodynamic equation. Let me do a perturbation of a homogeneous stationary state and see how this perturbation propagate on top of this homogeneous stationary state. So this is something that was seen in the previous talk. If you do a small perturbation, well, this small perturbation propagates according, linearly with the flux Jacobian. Right? So remember, the flux Jacobian was the derivative of the current with respect to density, so that's very natural that you obtain that. Right? So what this means, it translates into an equation for correlation functions. Perturbation will describe correlation functions. So correlation functions on homogeneous stationary state. They satisfy a nice constant coefficient linear equation, which you can solve explicitly. What you get is a delta function form. In fact, the meaning of this equation is that the two-point function of conserved densities at large scale in space-time and under appropriate fluid cell averaging, so under averaging in mesoscopic region in space-time, the result of that should be in general some generalized function of the form delta x minus at, so a function of a matrix is the flux Jacobian, so the matrix of derivative of current with respect to densities, times some other matrix C which represents the initial condition. That's just the susceptibility matrix, a two-point function of conserved quantities. Okay? So that's a completely general prediction from hydrodynamics. Obviously, it's hard to prove. It comes from kind of a hand-wavy argument, but it's very strong prediction about correlation function in space-time. Okay? Valued in thermal states, in GGEs, and for arbitrary conserved densities. You can, in fact, you can look at that in GHD and you get an explicit form for two-point function, for instance, in the Lieb-Deniger model, that involves the object that we've seen, plus some kind of a dressing operation, which I don't want to describe, but essentially this is something you can calculate on a computer very easily. So you can predict correlation functions, say energy density two-point functions, and compare with numerics and all that. And the phenomenology is very different in integrable system. You have a continuum of mode, while in non-integrable system you have discrete modes, where you will see just at certain velocities non-zero correlations. The non-zero correlation can have different structures due to which you will not see at this Euler scale, but you know in which direction they will be, essentially, right? So you can go a bit further and consider two-point functions of arbitrary local observables, not even conserved densities. And the principle here is the one of a hydro projection. Essentially, if you have a local observable there at some point xt, you see what it does on the fluid. Well, it changes the fluid a bit, but because of the relaxation, what it does, it can only change the conserved density. So essentially, you project it on conserved density. So you take the derivative of its average in GG with respect to the variation of conserved densities for O1 and O2, and then you just evaluate the two-point function of conserved density. So again, this is another very strong prediction about correlation function of arbitrary local observables in GG and thermal states, okay, coming from hydrodynamics. You can make that quite explicit. So these are, of course, predictions. They're hard to solve in general. All these hydrodynamics involve local, entropy maximization and all that, which are to prove. But in fact, what's happening is these equations can be proven rigorously, at least in the context of quantum spin lattices. So it's possible to prove the hydro projection thing in short-range hypercubic lattices and the linearized Euler equation in finite-range quantum spin chains. So here, what you imagine is you have a Hamiltonian, which lies on the lattice ZD, or perhaps just on Z if it's a quantum chain, with some Hamiltonian density which acts on few sites around the site X. So say a spin lattice where on your lattice you have C2, say C2 space or Cn. Okay. And the state that you take, you can take it to be some kind of a thermal state of high enough temperature so that you are sure that correlations vanish quickly enough in space. So the idea is that you can construct from this the explicit set of hydrodynamic modes over which projection goes. So here, it's kind of non-trivial to know what are all the correct extensive conserved quantity, the hydro modes. Well, it turns out that you can explicitly construct this space of hydrodynamic modes purely using the two-point functions within the state of interest, within the thermal state. So what you do, you construct some kind of a sesquilinear form, which is just the space integration or space summation of the two-point function. This can be seen as a form on local observables, and then you can take away the null space of that by taking equivalence classes and then complete it by Cauchy completion, you get a Hilbert space, very much like what is done in the Gelfand-Nymark-Siegel construction, if you know about it. So you have a Hilbert space from that, and this is a Hilbert space of extensive observable. Time evolution on that Hilbert space can be shown to be unitary, and you can define the set of conserved quantities simply by all these elements of that space, which are invariant on the time evolution. This is a closer space. There's a projection of this Hilbert space on that closer space. And this is what I claim, the correct set of hydrodynamic modes. The Hilbert space correctly represents the hydrodynamic modes. Now, why is that the right claim? Well, consider the Fourier transform of your two-point functions. And for this Fourier transform, you can prove these two things that I talked about, so the hydrodynamic projection and the linearized Euler equations. So the Fourier transform of two-point function is something that easily can be shown to exist. If you look at it at a large wavelength, so small wave number, and large time, take the limit, this object can be shown to satisfy the hydrodynamic projection principles. In other words, you evaluate that on any observable A and B. The result is continuous in that Hilbert space of extensive observable. And the result actually is the same as the result of the projection of these observable on the space of extensive charges. In other words, you don't need to know all the correlation functions, you just need to know the correlation functions of conserved densities. So this is something that is completely general in lattice models. So the lattice model may be integrable or not, chaotic or not, constrained or whatever, is always true. The only thing that is not trivial is the space of extensive conserved quantities. The other thing that's always true is, so in general, this space is state dependent, but here it is unambiguously defined and complete. In fact, it's a refinement of the concept of pseudo-local charges that was introduced by Prose in the context of integrable models. Okay. Now, you can also go further and prove the linearized Euler equation, so the propagation equation for two-point function. Here it takes the form of a derivative with respect to the Fourier parameter in some quantum chain. And what you show is that the two-point function is differentiable and the derivative is exactly given by the summation with the flux Jacobian, which is just the expansion of the projection of the current on the basis of extensive conserved quantity, essentially. So that tells you that the structure of hydrodynamics is very general, does not require to know a lot of things about the model, holds in a very quantum spin chain with finite range interaction. The only thing that is non-trivial, of course, is what is the space of extensive conserved quantity on which you project. And that is model dependent, and that supposedly in chaotic system is going to be one-dimensional or kind of finite dimensional, while in integrable system it is infinite dimensional. Nevertheless, the structure always is correct. Right? Yeah. Now you can look at that in free fermion models and construct everything explicitly, and everything works. So basically, the extensive conserved charges are nothing else but the fermion number, the mode numbers at mode P. So you can show that this is correct. So in other words, this formal construction reproduces what you would find from generalized hydrodynamics. Right? So in particular, reproduces two-point function of density of fermions. Okay? So the construction is correct, but of course it would be nice to construct it beyond just a free fermion model. Okay? In fact, you can also ask the question, what happens for a correlation function of fermions? Now, according to hydrodynamic projections, because fermions have zero projection on the extensive conserved quantity just by fermion conservation, the hydrodynamic principle tells you that the two-point function of free fermions in space-time is just zero at large space-time separation. That's what hydrodynamics tells you. Okay? Now, this is a bit disappointing because we know that two-point function is not zero. It's one of the square root of t times something. But something is oscillatory. You can get that by a simple saddle point analysis. Okay? So we have to remember that the predictions of hydrodynamics are correct under fluid cell averaging. So in hydrodynamics, you forget about any oscillations. You average fluid cells, so that gives zero, so this is actually a correct result. Okay? Now, but there's one observation which is very important, which is that in fact, you can apply these hydrodynamic principles beyond zero frequency and infinite wavelength. You can, in this formal construction, replace your time and space translation by oscillatory space-time translations. These are still unitary operator on your Hilbert space. The Hilbert space are constrained. They're still unitary operator, so everything works. And can redo the full construction of early hydrodynamics based on oscillatory space-time translation. If you do that, what you get is hydro projection on arbitrary frequency and wave number, and you get back in the free fermion model you get the correct prediction that you have oscillatory behavior of fermion two-point function in space-time with the right oscillation, with the right dispersion relation. In other words, you can do hydrodynamics not just at zero frequency and at zero wave number, you can do at arbitrary microscopic frequency and microscopic wave number. You just have to, replace your fluid cell averaging by oscillatory fluid cell averaging. And there is a whole parallel hydrodynamics for every frequency and wave number. In particular, there's the concept of extensive charge and projections and all of that for arbitrary frequency wave number. Okay, so this is about kind of how, so it shows that hydrodynamic principles are even more general than what you have thought before. It goes beyond zero frequency wave number and applies to every quantum spin lattices and quantum spin chain. Okay, so that's that was part two. My part three is about what hydrodynamics can go beyond also linear response. That was just linear response, right? Two-point function, linear response. And it can describe fluctuations as well. And here, so this kind of maybe older results, but so what you look at here now is you still have your conserved quantities and your, whoops, show what happened there. Yeah, conserved quantities and conserved currents, and you're interested in, for instance, the large deviation function of transport, through an interface. So natural quantity to look at is the large deviation function for the total current, see the current of energy, transported through some interface between time 0 and time t. Okay. So it's something that replaces, let's say, the large deviation function of total energy on some region, which will just be kind of standard thermodynamics. So this is something that goes beyond standard thermodynamics towards the time regime instead of space regime. Okay, so towards time instead of space. So f of lambda encodes information about fluctuation of, say, energy being transported. And turns out that this f of lambda, again, is completely determined by other hydrodynamics data, in particular by this flux Jacobian. F of lambda encodes, if you do the expansion of that, it encodes not just 2-point function, but 3 and 4 and 5-point function integrated of the current. So this is higher point function. Okay? And again, higher point functions are still fully encoded in early hydrodynamics. Okay? So how does it work? Well, you can think about, so the physics of that is more interesting if you think about non-equilibrium steady state. So this is a typical formulation of non-equilibrium steady state. We have t left and t right. Initially, then you evolve on large time, look at large time limit, and so essentially you look kind of here what the state is and want to have the properties of the state, in particular the fluctuations of the currents there. Okay? So essentially you have particles going from left to right, and look at this, their large variation theory. Okay? So this f of lambda, of course, been studied since a long time, is well known in free fermion model what it is. Here's the formula with some kind of Fermi filling fraction describing the left and right bath. Okay, so that's formula that you can find from using free fermion properties. And it's also known this formula satisfies something which is called Cohen-Galotti, or perhaps Crookes relation. I don't remember what's the right name exactly, but it's a symmetry relation for the function f of lambda, which gives a lot of non-trivial relation between the cumulants, some kind of non-equilibrium fluctuation relation. Okay? And that formula is supposedly extremely general, not just in free fermion, but in many different many-body systems, supposedly. Okay? So it's an interesting quantity to look at. Now we've looked at that. Little pause here. Yeah, I think good. So we've looked at that with the knee in conformal field theory, where we constructed the exact non-equilibrium steady state, which is relatively simple, which is just a determinization of right and left movers independently. And we've obtained an exact formula for this full counting statistic. Now this is interesting because we obtained that using kind of real-time methods in conformal field theory, but it was then later on proved by Christophe and Carole here in Lyon properly by using non-trivial conformal field theory method, and in particular conformal welding, if I remember correctly. So this is kind of a very nice general result that was in the end proven rigorously by Christophe, which was very interesting for us. Okay? Now, it turns out that this f of lambda, in the end, has a purely hydrodynamic origin. So there's a formula in CFT, but this formula in CFT is nothing else but a special case of a general formula, which is purely hydrodynamics. So if you apply this hydrodynamics to the hydro of CFT, you find the formula that we had with the knee and proven by Christophe and Carole. So what's the general formula from hydro origin? Well, here it is. It is relatively simple. So this f of lambda takes the form of an integration over some lambda prime, from 0 to lambda, of an average current evaluated into a lambda prime dependent state. So it's a kind of a GGE now that depends on this extra parameter. And what is this GGE? Well, this GGE is obtained by looking at a flow equation where the beta, is the inverse temperature, satisfies the equation d lambda beta is minus sign of the flux Jacobian. So again, the flux Jacobian is involved there. It appears somehow magically in this formula. But what appears is the sign of the matrix. So you need to take the sign of its eigenvalue and kind of, in the right basis. Okay, change the basis to its eigenbasis. And this describes essentially the full f of lambda. If you apply that to CFT, you recover the CFT formula. What it says is that actually when you put the time integral of the current there, you actually modify the state in a non-trivial fashion. How you modify the state is given exactly by this flow equation. Okay, so this is something we derive, and we derive that using hydrodynamic projection principles. The hydro projection that I showed are the ones you use in order to obtain this formula. So this paper, so I don't know if I should have mentioned that, but actually Christophe was suggesting it for a prize, which has got the prize of the best paper in AHP. So thank you very much, Christophe, obviously. And it's something that we discussed a lot with him, and Christophe had a lot of nice ideas about fluctuations, which at that time I didn't fully understand, but I'm slowly starting to understand. And maybe in the next year or so, some more results will come, and not just about that, but about more general fluctuations using hydrodynamics from Christophe's ideas. But here what I wanted to say is simply, well, so this is some general formula which can be applied to many, many different systems, not just Hamiltonian systems. So we've applied it to TSEP. We've seen a talk about TSEP today. So this is a stochastic particle system, but it still has a hydro description. You can apply the formula, and you cover the formula obtained much earlier by other people and by proper kind of microscopic calculation. You can also apply it to the hard spheres in one dimension. We've seen talks about hard spheres, right? So hard spheres in one dimension, they're actually integrable, they're then described by GHD. So you can apply this formula to full GHD, calculate the cumulants and check numerically, and they work very well. You can apply to free fermions, you reproduce Levitor-Flesovic formula, to CFT, you reproduce our formulas, and even to cellular automata, something called the Box-Bowles systems. And people have shown in that cellular automaton that the GHD results, is integrable again, do reproduce the GHD results for that formula, do reproduce the kind of microscopic calculation. So that's all I wanted to say. So basically, conclusions, so sorry, it's a bit long. So three things: generalized hydrodynamics, which is hydro theory for integrable systems, has been developed quite a lot, has been applicable to many, many different situations. It shows that actually hydrodynamics goes much beyond the standard realm of chaotic systems. Hydro projections is something where you can get mathematical results there, which is very nice. You essentially get mathematically the fact that you have a mixing or thermalization towards a very precisely defined set of hydrodynamic modes. It'd be nice to work this out more explicitly in other models. And in fluctuations, where we went a bit beyond what I showed. We developed this ballistic microscopic fluctuation theory, which in principle describes large deviation theory for many extensive observables. But there's still a lot to be understood from the hydrodynamic perspective. Thank you for your attention.
Thank you very much, Benjamin. Other questions?
So do I understand correctly that all of this was one-dimensional?
Yes, sorry.
What about higher dimensions?
Yeah. So, no, of course, I should have mentioned that I'm restricting myself to one dimension mostly here, except for the hydro projection result, which was in arbitrary d-dimensional hypercubic lattices, spin lattices, so this was d-dimensional. But I certainly expect, many of the results to hold in higher dimension. Now, for integrable systems, you'd have to work out higher dimensional integrable systems properly, and currently, there's not enough, as far as I understand, not enough data to apply what I've described here. But eventually, I'm hoping that this will also be possible. For fluctuations, we haven't worked it out yet, but I suspect it will be possible. But of course, in higher dimension, many is quite a different phenomenology, as we've seen in many talks before. So I'm not completely sure. I mean, one will have to see.
Hello. Yes. I have a small question related to your second point. So can you comment on the effect of like small integrability breaking terms that you might have in experiments and stuff? So
yes, indeed. Thank you. This is a very good question. So I showed you at the beginning the Liouville equation, which is kind of the collisionless Boltzmann equation. So you can add the Boltzmann collision term, right? Well, likewise, you can add the Boltzmann collision term on the GHD equation, which will represent integrability breaking. So Boltzmann collision is actually integrability breaking. You break the integrability of free particles, or in GHD you can break the integrability of interacting particles. This Boltzmann collision term is actually rather complicated. You have to know appropriate form factors of your integrability breaking term, whatever it is, right? It can be some particle loss, it can be some, well, that kind of things, okay? So you have to know these form factors, and they're hard to calculate right now. So right now there's a formal equation, let's say, like a formal Boltzmann term that we can write, which we can just evaluate in very simple cases, but it's still very much up in the air to make something more precise out of that. Yeah, but maybe I should say, so typically in experiments you have integrability breaking, obviously, but the effect is very small, and the time scale of that integrability is much longer than the generalized thermalization timescales. So GHG is actually still working quite a lot. It's a small modification of GHG.